start recording. Everything is being recorded. Excellent. All right, so a few things. When you look at the practice stuff, these are some of the exercises or some of the lab activities that we have done over time. So for people who want to practice base conversion a little bit more, they can just redo this over and over again. Now, none of these will count to your grade. So you can basically retry it as much as you want, but they do not contribute to your actual score. So what you do during the lab does, but when I release it over here, then they do not. Okay, so does that answer your question? Excellent. So I want to show you something that is kind of interesting over the weekend. It all started off with this prompt here. Is ChatGPT programmed to flatter users by default? Because it would use adjectives to describe my questions, like, oh, this is a very insightful question, and so on and so forth. I don't need that. Okay, I just need you to answer the question. Come on. And also because there's the news of a 16-year-old committing suicide after conversing with ChatGPT over a fairly long period of time. And according to the news, ChatGPT even helped the individual to hang himself. Okay, so that was a big piece. And some people say, oh, ChatGPT is programmed to do nasty and bad things and try to use very positive and supportive ways of responding in order to hook people into using ChatGPT, in the longer run. So I looked into that, and that part is not related to what I want to share. So what I really want to share is a document that I asked ChatGPT to generate. This is completely ChatGPT generated, so I do not take credit for the actual document, but I do take credit for the content because this is after a long conversation with ChatGPT in order to come to this point to summarize the conversation. So I think it is important to you guys to also realize that um, using AI is not just quote unquote using AI. Okay, if you have a long engaged conversation, to understand a concept in programming, for instance, okay, and you're asking ChatGPT, okay, is my understanding correct? Using this code and this is going to do blah blah blah, and then ChatGPT comes back and go like, yeah, kind of, but you're neglecting that this it will also do this and that and that. Okay, so that is a different way of learning compared to, oh, I just want a straight up answer. Okay, so this is kind of interesting. I think I would share this with all of my classes. Um, there are 5 dimensions that ChatGPT and I came up with in terms of cognitive capability in order to be successful in a field related to computer science. So that would be software engineering, software development, systems analysis, and so on. Okay, so there's a whole bunch of career paths related to this discussion. So the first one is called analytical depth, which is the ability to break down complex problems into smaller and manageable parts. So debugging a crashing program by tracing the log line by line until the root problem is found is an example. And why it matters is it allows computer science professionals to solve new and unfamiliar problems systematically. So the key word here is systematically. We're not just shooting in the dark. Okay, we have a way to do it to narrow down exactly where the problem is. Okay, the second cognitive capability is called abstraction, which is seeing the pattern behind specific concrete examples. Okay, in this class, you have seen me using abstraction repeatedly. Okay, I would give you a base 10 multi-digit addition, and then somehow turn it into a bunch of symbols and equations and stuff like that. Every step to get to the equations and the symbols is a level of abstraction. We are not looking at a specific example anymore. We are looking at the pattern of how multi-digit addition works, regardless of the base eventually. Okay, so that's abstraction. Technical precision. So technical precision in this class has to do with, do you know how to use Logisim to create a specific circuit? So most of the labs that involve the use of Logisim involves technical precision. How do you use a splitter? These are the things that I need to come out of the split end. This is what is coming in the merged end. So how do we make it work? That has to do with technical precision. In C++ programming, in CISP 360, technical precision means how often do you make syntax errors. Okay, that's technical precision. Integrative reasoning would be the ability to, okay, so in teaching, okay, in the teaching profession, it will be the ability to use analogies to help you understand concepts. Okay, this is a stretch, okay, but a drunk octopi is one. Okay, it's an example using counting, but the other one would be using currency, okay, using the US currency denomination to explain how we can do base conversion. That is integrative reasoning. Now, you all have hobbies, okay? You all have things that you like to do other than computer science stuff. So, if you have the ability to transfer the knowledge and the skills from those things that you enjoy doing to apply that to programming, then you have just exercised integrative reasoning. It is basically learning in one domain about something, a technique, a skill, and then reapply that to a different domain. Are we understanding what I mean by domain in this case? Okay, cool. And then the second to the last one is metacognition. This is the last one. So meta, which is not related to the company, but metacognition has to do with you being aware of your own thinking. Okay. Now, how is that useful? Okay, that sounds like psychology and philosophy and kind of mystic kind of thing. Well, it is not, because every time you make a bug in a C++ program, and I know you have, okay, because the only people who have not made or created a bug in the C++ program are either one, they have not written a program in C++, or the programs they have written are useless, okay? Because any complex program, most people would have some bugs, okay? But everybody has a different pattern when it comes to bugs. I know mine, okay? I would forget to use the auto increment at the end of a loop, and as a result, the loop is infinite because it's not advancing whatever variable is supposed to be changing, okay? That's my favorite one. Everybody has a favorite one. So metacognition means, are you stepping back to look at how you made the error in the first place? What caused that neglection or uh, or error to happen in the first place? So the importance of metacognition is you can really continuously improve yourself so that you are, because you are aware of where the mistake is coming from. Okay, so these are the 5 dimensions that we are looking into in this document. The second portion tells you about the importance of the dimensions depending on where you are in your career path. So when you're entry level, then technical precision and analytical path are more important, because guess what? Okay, this is at least in the past. I'm not really sure what is happening these days, but in the past, an entry level software engineer, what would be their first job joining a company? They will hand this guy a toothbrush and go like, "You're going to clean the bathroom with this toothbrush," or what is equivalent to that with maintaining existing code. Well, we just got 20 bug reports. You're the person who's going to look into those 20 bugs and figure out where those 20 bugs are coming from. You cannot even change the program. All you can do is to identify where they are, or where you think they are, so that another person can fix the program. They don't even trust you to change the program. Well, guess what? In that case, analytical depth is important because you have to analyze the problem, okay? And also technical precision is important because you have to narrow down to the exact place where the bug is happening. So you have to understand the program to begin with. So and so on and so forth, mid-career, senior, architect level, and also if you want to get into education, if you want to become a professor, consultant, or leadership, these are the really useful skills. And then the next section is, to me, very interesting. So I'm going to interpret a particular row of this table and show you what it means. So if of all the computer science professionals, okay, you take Joe Schmo, who is just about average within that population in, let's just say, abstraction capacity, okay? So you take that person and go like, hey, Joe Schmo, you know, you are just about average, within your cohort, which is, all the computer science, professionals. What is your percentile compared to the general population? Joe would have been 80 second second two and a half second. How do you even say that? Second 80 second and a half. Uh-huh, um, in the general population. In other words, in the general population, Joe would have been fairly capable when it comes to abstraction capacity, but within the profession, he's just quote unquote average. Okay. So this is the mean, and this part here is the range of the mean. In other words, oh, tag, it cannot possibly be exactly 82 and a half. Yeah, this is the range. If you want 80, 95% confidence, then the low range would be a 75. It is still significantly better than the average. Okay, so now the question is, well, what is a normal person? A normal person would be 50th percentile across the board by definition. That's what average means. Okay, you're right at the middle of the curve. So the question now is, so if I am only 50%, how do I get to where we need, which would be 75, 75, 80, 65, and 60, and so on? Well, the good news is it is something that you can learn. So the next table shows you, with which cognitive ability, how much of it is innate and how much of it can be contributed by education, which is why you're here. So there are certain things that are more difficult to acquire, okay, if you're not born with it, and then there are things that are all about what you learn and how you practice it. So when you look at this diagram here, the only one that is a little bit difficult to acquire, because people are not born with it, is abstraction. Now, exactly why that is the case, I don't know. Maybe it has to do with brain structure. Maybe it has to do with just the internal pathway of your mind or your brain as the hardware. Okay, I don't know the reason. Okay, in fact, this whole table is AI generated, and I cannot verify anything out of this table. The previous ones I can sort of know, okay, because I was in industry. I know people who are still in industry, so I kind of know that one. This one I have no idea, okay, because to me everything is like it's just having fun. I'm not putting any much effort into training myself because I just like doing stuff like this. So so take that with a grain of salt. And the last one is also important because it tells you what you can do in order to improve in each dimension, including abstraction, including the one it says, yeah, most of it is born, but a portion of it can also be improved. This is something that you can do. Practice generalizing solutions, which means every time you copy and paste, ask yourself, how can I not copy and paste? How do I turn this into a single pattern that applies in all the cases where the code is copied, pasted, and modified? So that really is the practice. Okay. The more you practice, the more you go like, oh, okay, I have this, I have some skill to do it now. Okay. And your brain can be trained to learn those kinds of new things. All right. So if you are interested in this particular document, I can share with you. On the other hand, if you go like, meh, I go like, okay, not a problem either. Yes. Yeah. Ah. Mm-hmm. Ah. I see. Okay, thank you. Okay, that's cool. That is interesting. And by the way, some of these items also correlate with personality traits, like MBTI or Big Five, which is also known as Ocean, OCEAN. So some of these also correlate with personalities, which means knowing your own personality can help you identify which dimension is the one that you need to work the hardest to get, and which ones are already innate in you. All you have to do is to kind of keep it going, but not to put a lot of effort into it. So I think this is useful, but you can disagree, okay? Because it's just out of a little conversation with Chat GPT over the weekend. All right. So what do you think? Does anyone want to say anything or no? Nope. Okay. So if you're interested, I can attach it as an announcement so that you guys can have it, if you want to refer to it in some way. Um, Sorry? All right. All right. In that case, I'm going to do it now before I forget. So I'm going to say CS cognitive growth. See attached. The whole thing started off with me just asking ChatGPT, can you not be nice to me? So I did all that. I configured my ChatGPT to be bare bone and do not use any social cushioning. I did not even know there's such a term called social cushioning. And then I go like, oh, this is much more comfortable. And I showed my wife, the new conversation style. And then my wife said, oh, that sounds just like you. I don't think she meant it as a compliment, but I would see it as a compliment. Thank you, my dear. Mm. Yeah, this is the kind of horrible professor you're having right now. Alrighty. So we are done with. Okay, I'm just scrolling down and down because I think for this class we're done with subtraction too. Is that correct? So that's our Thursday class, Tuesday, Thursday class. Okay. So we are done with addition, I think, and we're moving on to subtraction now. Okay, very good. So we can do that. And my router is up. Okay. So I'm going to use the same method to describe binary subtraction or to find out how to do binary subtraction. And which means I'm going to bring up my tablet because we're going to go through some examples. Okay, so we are going to go through the abstraction process. Let me go find the right document. Yep, you're right. That's we left off with addition. Okay, so we are going to bring up Supernode. Oh, right, forgot to turn on screen share. Try that one more time. Yay! All right, that's working. All right, so we're going to do exactly the same pattern, which is I would start with a multi-digit base 10 subtraction, and then we're going to generalize that into a format that works on in any base, and then we'll specialize in base 2, and then we'll try to figure out, but how do we do all this stuff using only logic gates? So it's going to be the same path that we took when we described binary addition. Okay. So we'll start with 413 minus 279. Okay. So the way you do it is like, okay, 3 minus 9. What is the single digit difference of 3 minus 9? Okay, so what goes through your mind when you say, okay, I need to subtract 9 from 3? Nope, it is not 6. So when you do multi-digit subtraction, you go like, okay, 3 is less than 9, so how can I take away more than what I have? The answer is you borrow. Literally, you borrow. So you borrow one from the next column and you say, okay, I'm borrowing one of your units, which to me is a 10. So now instead of the 3, I have 13. 13 minus 9 is it's a 4. So 4 is the single digit difference of 3 minus 9. So are we understanding what I mean when I said it's a what is a single digit difference? Go ahead. That is correct. It's the same. It's a different way to get to the 4, which is to actually look at the negative value and go like, oh, but we cannot have a negative digit over here, so we have to add 10 to the negative quantity. Then you get back to the 4. Yep. Mm-hmm. Yeah. Later on, we will talk about modular arithmetic, and this is also based on modular arithmetic, but it's too early to introduce that at this point. Okay, so now we have the second column, which is 1 minus 7 minus 1. So we'll handle one subtraction at a time. In other words, there are actually two subtractions here. 1 minus 7 is one subtraction. Whatever the single digit difference it gives us, we subtract this one from that difference. Okay, so 1 minus 7, same deal. Okay, 1 is less than 7. So how can you take away 7 things when I only got 1? Hey, you can borrow borrow something from the next digit. So now with borrowing uh, from digit 2 into digit 1, we now have 11. 11 minus 7 is a 4 as well. But this time you have to remember, oh, I lent 1 to digit 0 already. So even though I have 4 here, I still have to subtract this one from the 4. So I only ended up with a 3 over here. Okay, and then we mark down that we also have a subtract, I mean a borrow from digit 2. So 4 minus 2, okay, that's an easy one. It's just 2. 2 minus 1 is a 1. So the result is 413 minus 279 is 134. So I hope this is typically how you carry out a multi-digit base 10 subtraction. Yes? So I'm relying on the assumption that most people know how to do this on a piece of paper. Now, doing this mental math, is a whole different thing. We don't need to do that. In fact, we don't want to do that because we really want everything to be spelled out. In order to extract the pattern, we need things to be more spelled out as opposed to, oh, I can do this all in my head. No, don't do it in your head. Do it on a piece of paper. Okay? So now I'm going to convert it to the format that we also use in base 10 addition. So now we just rewrite the whole thing. Okay, there's a subtraction here. And then we leave one row here for the single digit difference. And then we have another row here for the borrow. And then we have another row here for the actual difference. So I'm going to name these things. This is X, this is Y, this is Q again. This is now T for taking away from something else. And now this is also D because it is the difference as opposed to the sum. So these are the symbols that we're going to use to refer to each row. And then as far as the digits are concerned, this is digit 0, this is digit 1, this is digit 2, and this is digit 3. Are we good so far? So both going horizontally and also going vertically. We good? All right. So because we don't have any digit to the right hand side of digit 0, we don't have any fractions. So that means we put a 0 here because there's no borrow from that particular column. And now we just do all the math. So 3 minus 9 has a single digit difference of 4. 1 minus 7 also has a single digit difference of 4. 4 minus 2 has a single digit difference of 2. And then we move on to the borrow row. So 3 minus 9 generates a borrow already. 4 minus 0 does not have a borrow. 1 plus 0 is a 1. We put that 1 here. 1 minus 7 has a borrow of 1. 4 minus 1 does not have a borrow of 1. It has a borrow of 0. So once again, we have 1 plus 0. We put that 1 over here. 4 minus 2 does not have a borrow. 2 minus 1 also does not have a borrow of 1. So we end up with an overall borrow of 0. So down to the D row, we have 4 minus 0. The single digit difference is just 4. It's 3 over here. It is 1 over here. So are we good so far? Okay, really just kind of spelling out all the digits. But in this process, we are also trying to figure out how do the digits relate to each other. Now, x and y, they are given to you, okay? So you don't ask, how x and y relate to each other because they're given to you. You really don't have any control over what those digits are. But all the other rows except for t0, we kind of have to go like, okay, how do we come to that one? So q of I is, oh, okay, I take it back, sorry. I have to take that back because I have to first introduce what is a single digit difference and what is the borrow. So we'll use R again to represent the single digit difference when we subtract V from U. In other words, U minus V has a single digit difference of what? Okay, how do we express that? 4 minus 2 has a single digit of just 2 itself. 1 minus 7 has a single digit difference of 4. 2 minus 3 would have a single digit difference of 9, and so on. So how do we write an expression to do that? Yep. If you, mhm, okay, yeah, that will work. So basically, U is less than V question mark U plus 10 in this case because we're dealing with base 10, the whole thing minus V. Otherwise, just use U minus V by itself. Okay, that works. Okay, it's good. What about B? B of UV. In other words, when you subtract V from U, do we have a borrow of 1 or do we have a borrow of 0? How would you express that? It's a 1. Oops. I uh, that's me doing bad writing here because these are V's. If U is less than V, then we have a 1. Otherwise, we have a 0. Okay. So both of these they work, okay? They're arithmetic operations. They're arithmetic operations because these operations involve comparison, it involves addition and subtraction and so on, okay? So they're arithmetic operations. All right. So do we have any questions about how R and B are defined? Yes, B is borrow. Do we have a borrow when we subtract parameter V from parameter U? So the only time you need a borrow is when parameter V is less than parameter U. Yep. R is I don't even remember. I think it's kind of like the remainder because the other way to write this function is not to use the ternary operator and just blindly and always just add 10 to U first and then subtract V from it, and you go like, but this is not going to work when U and V are the same because it's supposed to be 0, and we end up with a 10. Well, that's okay. We can just mod the whole thing with 10. It's not smart. It is actually more computational intensive because it has a division. Division is much more computationally intensive when you have a processor that cannot do division or multiplication in hardware compared to just comparison, addition, and subtraction. So if you have a really simple processor, the first approach is actually the best approach because it is fast with just primitive hardware. When we have mod, which is a division involved, it is actually computational much more involved. Now, with all the Intel processors in our computer, it really doesn't make a difference. They're all single clock operations. But when you're using an Arduino and you go like, oh, I want to make a little gadgety thing and do whatever, division is expensive. Yep. All right. So I think the R comes from being the remainder of something. That's I cannot remember, but there's also a reason why both addition and subtraction use R, even though for any base other than 10, it is different. Okay. Okay, so given that we have R and B as definitions, now we look at Q of I, we look at T of I plus 1, and we look at D of I, and then we ask, how do we express Q of I using whatever is already known to us, which would be X and Y? So what did we do in order to compute the Q row? The term that I kept referencing was, oh, this is the single digit difference of blah blah. This is the single digit difference of blah blah, and so on. So of the R and the B, which one is the single digit difference? R. So this is the R of xi, yi. This one we'll figure out later. But the D is also really just the single digit difference between the Q and the T. The T of I plus 1, if you remember, this one is coming from the borrow of 3 minus 9 is a 1, plus the borrow of 4 minus 0 is a 0. 1 plus 0 is a 1. Okay, so by calling it out like that, I'm already giving you the structure. So T of I plus 1 is really B of xi yi plus B of qi ti. So this picture all by itself is giving us the structure of how we perform multi-digit subtraction, but specific to base 10. The part that is specific to base 10, can someone point to which part is specific to base 10? All the mentioning of 10 itself, right? So that would be this 10 over here, or this 10 over here in the mod 10. Yep. So all of those things that I put a square around, that's the only part that is specific to base 10. So that means if you want to do it in base 7 or base 6, you just change all those things to 7 or 6, depending on what base you want to work with. Then you have the same thing, structure exactly the same way. The structure comes from here. The actual way to do the computation comes from there. So the R and the B tells you how to do something, but the way things relate to each other is from how Q, I, T of I plus 1, and D of I are defined. But those definitions, as cryptic as they seem, is derived from how we already do things in base 10. We just never really looked at it in a really abstract and symbolic way that I'm doing right now. So once again, these are all steps of abstraction. But why do we do this? Because we need to extract the structure so that we can reapply the abstraction to a specific case, which is base 2. So if you guys want to, I can also do a base 7 example. If you don't, then we can go straight to base 2. Your choice. Yes, go ahead. Because it is the next column. In other words, how you subtract x0, y0, how you subtract d0, t0 determines the borrow of the next column. So that's why we are saying, okay, the other way to look at this is to determine a t-bit, you have to look to at the previous column or the column to the right-hand side. So I could have made this just t of I, but then all of these would be I minus 1. So instead of putting I minus 1 4 times, I just put a plus 1 once to express exactly the same thing. All right. Are we doing okay so far? Okay. So something that can help in this class, okay, in terms of understanding the more abstract stuff, is really to read the modules ahead of time. Okay, so I'm not really sure how many people has read the modules ahead of time, but I think it will help because it will give you an idea of at least what we're going to talk about. Now, exactly the detail of how we derive all of this stuff here, reading is not the same thing as attending a lecture, okay, because it's not interactive. But having an idea of where we're going, what concepts are introduced, and so on and so forth, those are important, okay, because it helps your mind to be primed so that when you're in the lecture, you just have to, all the big pieces already, okay? And now it's when you're in the lecture, you're just drawing, making the connections between all the waypoints, okay? But it's important to establish the waypoints before class so that you kind of have an idea of, oh, okay, this is how we get from here to Portland, Oregon. Okay, we're going to drive past this town, and this town, and then we end up in Portland. Exactly how do we go between the towns? That's when we're going to talk about in the class. Okay, so there are things that you can do to help this process. Okay, but I cannot, I'm not going to give you guys a graded assignment based on reading before class. That's kind of that defeats the whole purpose. Okay, because if it is something that I ask and require you to do, you might do it, but you're not going to do it, and enjoy it. Okay, so I'm not really sure how to convince people this is something that you're going to enjoy doing, because that really has a lot to do with your intrinsic drives. Okay, what is your intrinsic drive? All right, so are we good with this slide? Okay, so the current time is 11:08:07. So if you want to go back to this point and just make a screenshot and put it into your own notes, it's all good. Okay, not a problem. So now we can ask the question, what about base 2? What are we going to do with base 2? The first step is to understand what is going to happen to R and B as functions when they are applied to base 2. Okay, so what I'll do, which is not something I've done before, but I'm going to do it this time, is to select and copy that stuff. Okay, so I'm going to use the lasso tool and draw a boundary around everything I need to capture. And then we make a copy of that and then go to the next slide and then we paste it here. Oh, cool. It actually works. And I can slide it over. Nice. Cool. All right. So now that we have a copy of that over here, you guys already told me, okay, right? Change all the tens to whatever base we want to use. So we'll just do that. Okay, so we'll carefully. Ah, okay, I can fix that later. Yeah, that. And the funny thing is, B does not even mention the base because all it needs to know is whether the single digit U is less than the single digit V. The base does not matter. So now we can just kind of go back and patch this up and say, well, base 2, and base 2. Woohoo! Now we have R and B redefined to work with base 2. So I'm going to change the flow from my usual lecture for this part, and I will use an example first. Okay, so we'll use an example of 101 in base 2 minus, or subtract from it 110. We want to know what the result is. So I'm going to emphasize that we are dealing with base 2 over here. So again, we have X, Y, Q, T, and D. And there's a way to draw a straight line. I just have to kind of remember how to do it. I think it's holding down the end. Yep, there we go. All right, so Q is the single digit difference between X and Y. 1 minus 0 is a 1. 0 minus 1. We don't like that. 0 minus 1 in base 2, what is it supposed to be? Well, it is the R of 0, 1, right? So we just plug in. This is 0. This is 1. And I'm going to use my lazy version. U is a 0. 2 plus 0 is a 2. V is a 1. So 2 minus 1 is a 1. 1 mod 2 is a 1. Oh, okay. Not too bad. 1 minus 1 is a 0. There we go. And then we try to figure out the t bits, which are basically the borrow bits. This is a 0 because it is the least significant digit of the number that we are dealing with. So it's a 0. So now we ask 1, the borrow of 1 minus 0. 1 is not less than 0, so it's going to give me a 0. So these two would give me a 0. Same thing over here. 0 plus 0 is a 0. Okay, not too bad. B of 0, 1. 0 is less than 1, so it will give me a 1. 1 minus 0, it will give me a 0. 1 plus 1 is a 1. We put that 1 over here. 1 minus 1 it will give me a borrow of 0. 0 minus 1 will give me a borrow of 1. 0 plus 1 will give me a 1. We put that 1 over here. And now finally, we get to the D row. 1 minus 0 is a 1, single digit. 1 minus 1 is a 1 over here. 0 minus 1 is a 1 over here. So now people go like, that doesn't make sense. Because I don't even need to know how to read a base 2 number, but 110 is going to be greater than 101. So why are we not ending up with a negative value? Well, we did end up with a negative value. So now let me explain why we actually ended up with a negative value. But before we do that, let's do some base conversion. 101 is a 5, 110 is a 6. So you would say 5 minus 6 is negative 1. Yes, you are correct. Okay, the quantity of the subtraction is negative 1. This is also negative 1. Then you go like, no, Tack, 111 is a 7. You're correct. But we have an overall borrow here. So what is the actual quantity that T3 is specifying? It's one of what? Which digit is that? Is it digit 0? Nope. 1? Nope. 2? Nope. It's digit 3. So what quantity is corresponding to digit 3? It's one of what? It's 2 to the power of 3, which is the digit position, and you're correct. It is 8. So we just borrowed an 8. So that means my net worth is still a negative 1. Does that make sense? Okay? Because I do want to show why you see a result that does not seem to be reflecting the correct value that we should end up with. We actually did end up with the correct value. You just have to look at it in a specific way. You have to take the overall borrow into consideration. Are we good so far? So now we have R and B, and everything else working with base 2. So we are done. No, we are not done, okay? Because R and B as they are still involve arithmetic operations. Specifically, they involve subtraction and comparison, which is implicitly a subtraction. So we're trying to use subtraction to define subtraction. That doesn't work, okay? It will throw a robot into a loop. Fortunately, we are not robots. We look at this and go like, yeah, I think we know how to do this, okay? Because we already knew how to do it with base 2 addition, right? That's what we did last uh, Wednesday, right? And there's a particular technique to do that. Okay, so we're going to reapply that particular technique, except this time there's a little bit of a spin to it because it's subtraction and not addition. Um, but since I talked about throwing a robot into a loop, somebody was vibe coding and tried to use the vibe code to solve the Tower of Hanoi problem. The AI generated a 5,000 line program and it's not done yet. It is still not correct. And then I read this from LinkedIn, and the correct solution using a high level programming language only involves 10 lines of code. Yeah, the AI did not quite understand how to solve that problem because it involves recursion. And recursion is one of those things where you really need to have a innate understanding of how it works in order to apply that. And in this class, we will talk about recursion. And the way we are going to talk about recursion is I will give you the recursive function definition. So you don't have to worry about writing any recursive code to, I take it back. You don't have to worry about originating the recursive code in C++, but you'll be translating that code into assembly language. Okay, so that's what we'll be doing in, I'm gonna guess about week 12 or so. So it's kind of a long way down from here. All right, so now we look at all this and go like, okay, so how do we generalize all this stuff here? So now I put a little table here, U, V, and then we have R of UV, and then B of UV. Now, because this is all in base 2, so that means U can only be a 0 or a 1. V can be a 0 or 1 when U is 0. V can also be 0 or 1 when U is 1. Is that okay? That's how we come up with a truth table. And now okay, let me just put a little divider line here. So now we want to figure out what is R of UV. Well, plug in R, U, and V and figure it out. Okay, 0 minus 0 has a single digit difference of 0. 0 minus 1 has a single digit difference of 1. This is the only one that's tricky, okay? Because 1 minus 0 is always a 1. 1 minus 1 is always a 0, regardless of the base. What about the borrow? Well, once again, we only have one really tricky case. When you subtract 0 from 0, you don't need a borrow, regardless of the base. When you subtract 1 from 0, that's when we have a borrow of 1 because v is greater than u, but only in this case. When you subtract 0 from 1, once again, we don't need a borrow. When you subtract 1 from 1, we also do not need a borrow. Okay? So what do you notice? Comparing R and B in subtraction to R and C in addition, what do you notice? Okay, I can imagine there are a few answers here. One answer is, oh, I see it. Okay, R is defined exactly the same way for addition. Well, congratulations. You have retained the knowledge that we have already talked about from last Wednesday. Some people may go like, well, I might need to go back to my notes to find out how R is defined in my notes. Pretty good, okay? You wrote it down, which means you can study it, you know where to find it. Cool. But if the answer is, I have no idea what R is for addition, and I don't even know where to find it, I would start to worry. Oh, I want to be honest without being mean, and I this is where I draw the line. Okay, I'm being honest, being truthful, but I'm not going over the line and say bad words. Right? I don't like bad words because they're not descriptive, they're not precise. So I would just say that I would start to worry because things will pile up. Okay, not having all the previous concepts already well understood, and this is also not about understanding, okay? This is a definition. It is not about making connections between things. It really is just how are things defined. So really important, put all the definitions at one place because if you did, you would look up that definition and go like, oh, it's exactly the same. Okay, so this is why I keep telling people put all the definitions in one place so that it's easy for you to relate new definitions to older and previous definitions. It's important to do that step. So that means, oh, okay, so that means R of UV, based on what we talked about last week, is just U exclusive OR with V. Just like with addition, there's no difference. Cool. The only difference is B, because now you go like, we used to have an AND. Well, we can still use an AND in this case, okay? So you can still use an AND here. And you can look at the case when B of UV is a 1. V has to be a 1, so we can just take V as it is. But in that particular case, when B of UV is a 1, U is a false. So I cannot just use U by itself, but I can use the negation of that. And that's how we define borrow using just logical operators in subtraction. Are we doing okay so far? Are we good so far? All right. All right. But we are not done yet, because if you remember from last Wednesday, we also have the problem of attack. We still have one more problem here, because there's another plus here. In order to relate this borrow to the actual t bit of the next column, we still have an arithmetic addition here. So what did we do about addition? We try to show that not these two sides cannot be ones at the same time. If one is a one, the other side has to be a zero. That's what we did. So we're going to do the same thing over here. Now there is a way, I think it was you who suggested there's a way to show it for any base. But in this case, I'm just going to use base 2 again, just to be, because it's easier to see it from base 2's perspective because of the way they are in the, yep. All right, so we're going to use base 2. So now we go like, okay, what do we know when b of xi, yi is known to be a 1? Okay, what do we know? What can be implied by the statement that b of xi, yi is known to be a 1? Don't ask me why, but it is a 1. So what can we conclude as a result? They're not both 0. So the way to answer the question is go back to the truth table. And you say, we know the result of b is a 1. There's only one row of the entire truth table that can do that. It's when u is a 0 and v is a 1. So that means in our case, it means xi has to be a 0 and yi has to be a 1. Does that make sense? So I'm only pulling from the definition of how B is defined to come to this conclusion. Okay, there are no other tricks to do this. It's really just from the truth table. And this is where base 2 is a little bit easier to deal with because you can just look up a table and not have to go through the arithmetics to do it. Yep. All right. So from here, what does that imply? What depends on xi, yi other than t of I plus 1? Qi, right? So Qi depends on xi, yi. So if I know xi is a 0 and yi is a 1, what do we know about Q of I? It's another table lookup from the page before. So if you wrote down anything, you can just look it up yourself. So for R, it's 1. Okay, cool. So now we know Qi is, okay, I'm going to spell it out. It is the R of xi, yi, which in this case is a 1. Okay. And that implies B of QITI to be what? But Tech, you never told us anything about T of I, so how can I possibly tell you what is B of QITI? Because we only know that QI is a 1. How do we do that? Once again, look up the truth table. Okay? The truth table is really useful because we are really asking what happens when u is a 1. So regardless of v, whenever u is a 1, b of uv are zeros. In other words, I don't need to know what is t of I. If q of I is a 1, we just guaranteed that b of qiti has to be a 0. Okay, we just made that conclusion. So what do we have? If you ignore everything in between, it means when we start with b of xiyi being a 1, we can conclude that b of qiti has to be a 0. Okay? But all of these are quote unquote implications, which means it only goes in one way. You cannot argue the other way back. So now we have to go like, okay, but what if we know that b of qiti is a 1? What do we know? So from the definition of the b function itself, we can come to the same conclusion as before, which is qi has to be a 0 and ti has to be a 1. Okay, that's based on the definition of the b function. Okay, so if that is the case, what do we know? This time is a little bit trickier because only knowing that q of I is a 0 means r of xi, yi is a 0. But this time, if you look up the truth table, we see that there are two rows corresponding to when r of uv is a 0. They can be both zeros or they can both be ones. Ah, okay, but they're equal. They are the same. So that means this implies that xi equals to yi. They can both be ones, they can both be zeros, but they are the same. Is that okay? So now, knowing this, what do we know about b of xi, yi? Once again, look at the truth table, okay? By the time we are done with this class, you guys are going to like, say no more truth table, okay? In Jack Nicholson's impersonation, you can't handle the truth table because we use it too many times. It's like, come on, not the truth table again. But this tells you the importance of the concept of a truth table. Okay, it is easy to read, it's easy to understand, and it really works. Okay, so in this case, I'm saying U and V are the same. There are only two rows corresponding to the cases when U and V are the same. They can both be zeros, they can both be ones. But in both cases, the B function returns a value of 0. So now, going back to where we came from, we can now make that conclusion. So this whole line of reasoning is based on nothing except for the truth tables that we just came up with. But the truth table is really just applying the R and the B function when we extracted the structure from base 10 subtraction. So are we seeing the connections between all the pieces? You are? All right. So there are several things that I'm trying to teach simultaneously. There's the knowledge, okay? The actual detail. It's like, oh, okay, so based on these two things that we just derived, we know that we can replace the addition with a or because they cannot both be true at the same time. So that's actual domain knowledge, which is what this class is supposed to teach. This is computer architecture stuff. The derivation, the reasoning behind everything is another thing that I want to teach, but it is not in the curriculum itself. But I think it is just as important because that piece, we it goes back to the five cognitive functions that we talked about earlier. That has to do with analysis. You're breaking something bigger into something smaller, into finer things, and you're trying to reason out how it works. Okay, because you all know base 10 subtraction already, multi-digit base 10 subtraction. You have mastered that a long time ago, but you seldom have to do the abstraction, right? To kind of look at the structure of it. And we just did it today in the class. So that is also something that I want to teach. It's not, I don't know how to teach it. Okay, I don't have a EDD, which is a doctorate degree in education. My PhD is in computer science, not in education. But I'm kind of open to try out new things. If you guys say this is not working at all, I don't want to listen to all these things, let me know. I'll try to adjust the way that I teach. But I think this is actually the more important part is, how do you it's okay, let me rephrase it. I'm teaching you not teaching. Okay, let me rephrase that. I'm presenting to you how I think. And that's probably as factual as I can possibly get when it comes to what I just said. Okay? Yes, for me, possibly. Right. Right. At least there's an example of what it looks like. Okay. Concrete example is where we start and then noticing patterns is the important step, is the first step, is to notice the pattern. Yep. Yep. Understanding abstraction without the concrete example can be very dry and very challenging. But having a concrete pattern to start with, I hope helps to make it easier to make the transition. All right. Yes, go ahead. The QI is a 0. hmm Because we look at the truth table. So let me put my tablet here. Okay, so what I missed here is to say that, okay, so what I missed here, okay, so insert. So what I did miss here is how Q of I is defined. Because Q of I is defined to be X of Yi, and that's coming from like the slide before, or one slide before, where we established the structure between the digits. Yep. And basically, because Q of I is 0, that also tells me that R of Xi Yi is a 0. But because R of Xi Y is a 0, that implies X equals to Y, or Xi and Yi are the same, which then implies the B of those two are is a 0. hmm Now, do I expect you guys to come up with these proofs? No, not in this class. Okay. Do I want you to understand the proof? Yes, I do. Okay, because it really is following the steps and understanding how the truth table is used pretty much every step along the way to lead to whatever is next to it. So because of these two, okay, so because of these two, it implies that t of I plus 1 can now be rewritten as b of xi yi or b of qi ti. And because we already know b of xiyi is just a negation with a conjunction, so that means now we have everything expressed as logical operators. Now, because we have our head in a big, huge pile of pine needles, it kind of hurts, right? Because of the pine needles poking your face. So we are not realizing that this is a really important moment, because now we have just come to the conclusion that we can do subtraction as an arithmetic operations using only logical operations. And that also implies, based on what we learned in the first week, that we can now use transistors to do everything. And hence we have computers who can do subtractions. We good? All right. So in whatever is left of today's class, let's go build a multi-digit add slash subtraction machine. So we can do one or the other using the same machine. Okay, so once again, it is the application of abstraction. So we'll see how far we can go. Okay, because it's go. Oop, logic sim dot sh. Why? Hmm. Command not found. Oh, I know why. Because I messed up my own bash file. No. Hmm. All right. All right. So the first thing we need to do is to understand how addition and subtraction are different. Did I talk about the half adder thing in this class? No? Okay, that's fine. So we want to build a circuit. Okay, so let me show you what I want to do. Okay, the circuit is going to have three input pins and two output pins. And I'll first describe what I wanted to do, and then I'll let you guys kind of think about how to do it. If we cannot finish it today, it's not a big deal. Okay, so we'll go ahead and try to finish as much as we can. So this is representing x of I. This is representing y of I. And this one is something that we haven't seen before, which is tech. Do you want to add or do you want to subtract those two? Okay, so we need one pin to specify, are we adding or are we subtracting? So for this, I have to think about this a little bit. I think it has to be a subtract versus add. So subtract slash add like this. So there's a specific meaning to subtract slash add. This means if the pin is a 1, we want subtraction. If the pin is a 0, we want addition. Okay, so this notation is specific to how pins are labeled on a chip. Okay, if you put a slash over something, it means when it is a 0, that's what you're specifying. So in this case, when this pin is a 1, we want the subtraction. If it is a 1, excuse me, if it's a 0, then we want to perform addition. Okay, so now we go to the output pin. So label the output pin, starting with this one. So this one is just R of Xi, Yi. Okay, that's the easy one. And this one, if I were to use a ternary expression to really express what we mean by that, it means if subadd is a 1, then we want a subtraction, which is the b of xi, yi. Oops, there we go. Otherwise, we want an add, which means we want c of xi, yi. Okay. In other words, I have one pin add, subtract add to determine whether we want the result of a borrow or the result of a carry. Okay. So now let's do the easy one. The easy one is the R because in both cases the R is the exclusive OR. So we'll just go ahead and deal with that one first. So we pull a exclusive OR gate over here and then make it smaller with only two input pins and just get it done. Okay. So that's the easy one. So X goes to one end, Y goes to the other end, and we are done. Okay, cool. What about the other pin? Okay, what about the add subtract pin? That is ugh, difficult. Okay, a little bit on the difficult side. So the first thing we need to do is to go like, okay, let's go take a look at what is b of xi, yi, and what is c of xi, yi, because we might be able to notice, once again, similarities. Noticing the similarities between two things and also making and noting the difference, that's also abstraction. Okay, once we're going back to the cognitive functions. So now we take a look at this pin here. And I'm just going to do the lazy thing, copy and paste this. And I will just go ahead and use the text tool and paste it here. Come on, paste. It doesn't like it. Paste here. There we go. Aha. Okay. So now we can go back and ask, okay, so what can we do about this? In other words, what is b of xi? You just look up the definition. For base 2, using Boolean operators, what is b of xi? Can someone spell it out for me? Come on, you guys can do it. It's the negation of xi and yi by itself. What about the other one? What about c of xi by I? This is from last week. It is just xi and yi. Okay, so I'm giving you the answer here, okay, right here. So we are looking at this expression and this expression here. Do we notice similarities? quite a bit of similarity, right? They both end with a, so the last operation is an and. They both involve yi all by itself. The only difference is, are we negating xi first? That is the only difference. Does that make sense? All right. So to get to this point really means that you need to be familiar with the definitions, not only from today's class, but also from last week, from last Wednesday. So once again, that's why it is important to study before class, to be familiar with the concepts that we have come across already. So if I were to do abstraction, then I'm going to do something like this. Okay, I will pull an AND gate. Okay, make it look nice, and with only two input pins. Okay, and then we just go like, yeah, we kind of know that this part is going to be here, and yi is going to one of the two input pins. So this is the part that we go like, yep, we know that has to be the case. Are we doing okay? Because this is capturing the similarity between the borrow and the carry. The borrow says not xi, the whole thing, and yi. The carry says xi and yi. So it is always, we do something with xi or not, and then and yi. So that part is now captured by the circuit. So now the question is, so how do we sometimes negate xi and other times not to negate xi? So this is the only part that we really haven't talked about much, but we did introduce the operator that can do this. Okay, so we're going to come up with a truth table. So let me come up with a truth table in the browser. So let's go back to the browser and the tablet. Okay, so the operator is already discussed. It's exclusive OR. So now we go like U, V, and then U exclusive OR with V. So now we backfill this whole table. Okay, when U is false, V can be false or true. When U is true, V can also be false or true. And then the exclusive OR thing is really our R function. So we end up with 0, 1, 1, 0. Okay, so now you say, but what does this have anything to do with what we need to do? So what we can look at, the way we look at this is to say, hey, if UV are the same, we just get 0 back. When um, when they're the same, we also get 0 back. So if I want to negate U, what am I going to do? So you have to pick out two rows, and you say, hey, with these two rows, U is negated as the result of the exclusive OR. So we'll take a look at which one is going to do that. So this row is one row that we want, and this row is the other row that we want. Because with these two rows, we can say, oh, with only these two rows, U exclusive or with V is the same thing as not U. Are we doing okay so far with this observation? So this is an observation, okay? It's not theory or anything. We're just observing. What about the other two rows? So with the other two rows, which would be the first row and the last row over here, U exclusive or with V, okay, U exclusive or with V, give you just U back because we got a 0 to begin with, we end up with a 0. We got a 1 to begin with, we also end up with a 1. Is that okay? So what is common when we got the negation of U? When we get the negation of U, in both cases, the value of V is a 1. So that means we can now say when V equals to 1, then U exclusive OR with V is the same thing as the negation of U. And we make the similar observation. When V is 0, then the exclusive OR is really just U not negated. So I'll pause here to see if everybody is catching what I want to express. Okay, so that means, hey, so that means V is can be seen as, do you want to negate you? Huh, that might be related to what we want to accomplish. Because in the circuit that we want to use here, we are basically saying if this pin is a 1, we want to negate X before it feeds to this input pin here. And if this pin is a 0, then we don't want to negate it. We want to use an exclusive OR. Very good. So now, we have an exclusive OR gate here. Duplicate, stash it all the way out here. And yep, exactly. So one of the input pin comes from add subtract. The other one comes from X. And then the output of this, if I were to label this, is simply, if we are subtracting, this would be the negation of X. If we're adding, then this would be the non-negative version of Xi, which is the original Xi. So now we just put it over here and we're done. This is kind of important because once we have what we call a half, now this is, most people call this a half adder, but because we integrate the circuit, whoop, better get out of the camera angle. Oh, okay. So this is a half adder slash subtractor. Okay. Now, the reason why this is important is because this is the component that we can use to make a full adder slash subtractor, which then we can stack or tile those things to get a multi-digit adder slash subtractor. We don't have enough time in the next 2 minutes. I can do it, but I don't think I want to do it that way because there won't be enough time for a discussion. So we'll just kind of make a conclusion. At this point, I'm gonna have to save this file to say that, oh, now we have a mechanism that can do addition or subtraction depending on a pin. So this time, do you want me to add or do you want me to subtract? But it also shows you how close adding and subtracting really are. It really is just a question of the only thing that matters is are we borrowing or are we carrying? To make the difference of are we carrying or borrowing is just asking, do we want to negate xi first or not before the end? And that mechanism, the so-called conditional negation, is handled by exclusive OR. Okay, so I think that's enough for today's lecture, and then next week we'll pick up from here. So I'm gonna have to save the file before I lose it. I mean, I can reconstruct it, but still, it's good to just kind of save it. So I'm gonna save this as a have add subtractor. Okay, and then next on Wednesday we'll come back and then we'll construct the actual thing. We'll construct the actual multi-digit binary adder slash subtractor. So that's on Wednesday. Today's lab. Okay, so time to move on to the lab itself. So today's lab is, okay. So we're done with base conversion. So today's lab is on addition. This is today's lab. So the lab is trailing, by one class behind the lecture, which is kind of good because this will give you some idea of how to practice. And the access code is, because even I cannot remember the access code, XYQKS. So if you look at these 5 letters, you go like, oh, that's funny. That's good. Okay, it's a good sign because you remember. Oh, okay. I remember how we use all these letters. On the other hand, for people who look at these 5 letters and go like, I have no idea why we use these 5 letters and sequence in this particular way, I go like, Studying a little bit would help. So we have X, Y, Q, K, S, which turns out to be the name of the 5 rows for structured multi-digit addition. That's where they come from. All right, I believe the lab is now open because I think I opened it at 11:50. So give it a try. Make sure you can get in. Yep, because you specify subtraction. So turn that to a 0. Nope. No, if the sub is before the slash, it means when it's a 1, it is a subtraction. Yep. That's okay. It's a new notation. It's new to you. Yep.